In this video, we'll be continuing the story of molar mass, where we had looked in the previous discussion of it. We'd looked at maybe a single atom, let's say beryllium, and we looked at the atomic number that it has of 4, but we also looked at that mass that was underneath that was written in a measurement having a decimal point, and we looked at taking and determining how many moles might be in 14.5 grams of beryllium. And we would always take the mass of 1 mole and say, I'll use that as a conversion. So for example, beryllium, if we look at a periodic table, beryllium has a mass in terms of 1 mole of 9.012. So we would write 9.012 grams of beryllium is equal to 1 mole. And that would allow us, as a conversion factor, to determine the moles of beryllium. The moles of beryllium. So we can use this in other ways. We can look at not just a single atom, but we can look at compounds. So we can look at beyond just an atom's molar mass, or atomic mass to be precise, but it's still the mass of 1 mole of silver is 107.9 grams. We can do this for compounds. So compounds are molecules made up of at least two different atoms. So water, for example, H2O. We can determine the mass of that mole of water. What would a mole of water weigh? So we can use that molar mass to convert any grams of water to moles. So we can use this as a conversion factor. 1 mole of water is equal to 18.02 grams. Now, if we have a compound, a salt here, this is an ionic compound, because it has the metal bonded to the polyatomic anion carbonate, we can find the molar mass of lithium carbonate by taking 2 lithiums together, adding them together with 1 carbon's molar mass and 3 oxygens. So we can take the mole amount of lithium and say, well, for every one of these, I have 2 lithiums. So 1 mole of this would be 2 moles of lithium. 1 mole of lithium carbonate would be 1 mole of carbon, and 1, again, mole of this would be 3 moles of carbon. So we can take and determine then the weight of each of these contributing species and add them together. So we'll do that. Our lithium, we'll look in our periodic table, is 6.941. So we can say 2 times the 6.941 grams is the weight of 2 moles, because 2 times the weight of 1 mole is going to give us that. So we would do that math. It's 13.882. We can do the same thing for carbon. Now I know that one, so times 12 grams. So no, it's roughly 12 grams. And oxygen is roughly 16. So we can say, you'd look at your periodic table to get the exact measurement. We'd say 3 times 16 is equal to 48. So we would add all this together. 48 plus 12 is 60. Plus that 13 would be 73.882. This would be the molar mass of 1 of these, because we added it all together, those contributing atomic masses. All right. We can do this with any compound, complex or simple. 9 carbons, 8 hydrogens, and 4 oxygens would be present in 1, compound of aspirin. It's C4H8O4. We can do that in a miltefosine is a drug used to treat those who have been exposed to the, amoeba that's in warm waters. It'll travel through the nose and infect the brain. It is the only treatment they have right now for early treatment of those who have been exposed to this literally brain-eating amoeba. But it has this complex structure. We could take all the carbons within this if we knew what MEs were, and you'll learn that. But we can determine all the carbons, and it would be 21, and the number of hydrogens 46. The one nitrogen here we see, there's 4 oxygens and 1 phosphorus. We can add up from the periodic table if we wanted. We could add up all those individual contributing atomic weights to this compound and its molar mass. It would be just the addition of all those. Now, the other way you can do is just look up on your phone miltefosine and type in molar mass. That's probably the easiest way to do it. But we can also work slowly. If we want to look at each of the atomic masses in the periodic table, we can do that. So here's the problem. It says how many moles of carbon are present in 0.185 moles of miltefosine. So we haven't asked for any grams from the periodic table. It's just wanting to know mole-to-mole relationships. So we can say for every 1 mole of this, I have 21 moles of carbon. So let's just say miltefosine, we'll just abbreviate it as 1 mf, 1 mole of it. We would have 21 moles of carbon. Would you agree that one of these gives us 21 carbons? 1 mole of this gives us 21 moles of carbon. So if we don't know what the number of carbons are in this much, we can just say, well, I have 0.185 moles of this MF. What would be the number of moles of carbon in that? We can just set up as a ratio. I know this for this, but I don't know this for that. So I can know 1 mole of miltefosine has 21 moles of carbon, but I don't know what 0.185 moles of MF has. I don't know the moles of carbon in that. So we just set up a ratio. What we know, what we don't know. So I can do that math. I'll do cross multiplication, because if we cross multiply, we know that this times this will be equal to this times this. So I'm going to do 21 times the 0.185, and I get, oh, okay, there are 3.885 moles of carbon in this 0.185 moles of miltefosine. So we again had to use that conversion. For every 1 mole of miltefosine, there's 21 moles of carbon. Then we'll do one problem involving conversions using molar mass, and we'll stop and let the rest of the work be done in class. So we might do 2 of these if we have time, but let's see what we can do with just this one, if it'll be enough to prepare us for class discussion. How many molecules of CO2 are contained in 5 moles of carbon dioxide? Now notice we're not starting with grams. So remember back before a discussion of test 1 material, we said if you know where you are, then you know where you need to go. We're not here. We're right here. This is where we are, is here. So I got an eyeball. I'm right here, and I'm going to not number of carbon atoms or oxygen atoms, but if we think of particles as usually like the molecule level, compound level, the number of CO2s. So we're really just going from here to here. We're not going that far. So I can just set this up as, oh, I have 5.0 moles of my CO2. They want to know how many molecules of CO2. I can say, oh, I remember the Avogadro's number. For every 1 mole of CO2, I have 6.02 times 10 to the 23rd CO2 molecules. Ran out a little bit of space, but I have this many number of molecules for every 1 mole of it. And we can just do the math then. And I'd said in class, if you're worried about the 10 to the third, don't worry about it. Just do the 5 times the 6.02. So we get 30.1 times 10 to the 23rd CO2 molecules. Let's do one more if we can. Just kind of using, as we've done before, conversions to answer some of the questions we need to answer. So again, we might use molar mass in some of our problems. If we start off with grams, we have to often use molar mass to get from grams to moles. We might have to do that here. Let's see. It looks like we will have to. It's saying how many grams of dinitrogen monoxide are in 1.5 moles of N2O. So here we're starting right here because it tells us how many moles we have, and we're going just one step up to grams. So kind of remember this rubric, grams to moles to number of carbon or compounds to atoms. We can use this. But we're just going from here to here. So that's one conversion, and it's a molar mass conversion. I need to know the moles per gram. Molar mass, the mass of 1 mole for this N2O. So I can start off with what I have. If you've been given the amount, the extent, we said we always start with that. So we have 1.5 moles of N2O. That's what they tell us we have, the extent of what we have in our hand. And we need to convert that to grams. So I always have whatever unit I have here. I have to put it on the bottom if I want it to cancel. And so 1 mole of N2O weighs 44.013 grams of N2. And now remember, where we got this is from the periodic table, taking 2 nitrogens, it's 14.01, timesing it by 2 and adding 16. That's where that came from. So once we have the equation set up and we know it's going to work, we're going to get the units we want, grams of N2O. We just do the math. So 1.50 times 44.013 gives us our answer, 66.0195, and we could just simplify that to 66.02 grams of N2O. And I'll stop there. We have some more that we can look at in class, and we will. We'll look at going from molecules to grams. So going a little bit farther, going from molecules to moles to grams. That's going to be 2 conversions. We'll see you in class. Bye-bye.